voice is audible, then I don't use the
Sir, mic. Mic.
Yeah, good afternoon, everyone. So, for the last 2 days, I think we are seeing another one of the topics. And today's topic, I think from the last 2.5 days, you are seeing different concepts about the concepts like what we call like multifunctional nanomaterials and other light, photon, photo, catalytic single crystals and all those concepts. But as I'm not a physics guy, I'm related to mechanical. So I don't talk on more on physics. Okay. So I'll talk on more a little bit. My area is on composites. So I'll start with composites and then relate those with nanocomposites, nanomaterials. Probably I think already Professor Ajim sir already explained about nanomaterials and the fabrication techniques. And you might have yesterday already you have seen the fabrication of nanomaterials. So I don't want to stress on those concepts. So I'll talk on materials, composites and nanomaterials. So my lecture, it starts with introduction of materials. Probably I think earlier speakers or else you have already studied about it. I'll start with the materials and take it to like evolution of materials, how it is started. And after that materials how modified to newer generations, and what right now, what kind of materials we are using, and how the advancements are happening in the materials in terms of nanomaterials. So this is outlines like introduction of materials, composites, nanomaterials, fabrication of composites, and then fabrication of nanomaterials, and a little bit characterization of the topics. So first I'll say like classification of materials. Everybody have a thought like classification of materials starts with engineering materials. We start with ferrous, non-ferrous, composites, plastics. So all these are general classifications. But I'll start with this slide. It shows like the materials are starts with two kinds. One is man-made materials. Another one is natural materials. These are natural materials. In the nature, we have a different kind of materials. Few materials modified by a man and then developed the materials. Whatever we studied, like for example metals, polymers, ceramics, all these are man-made materials. These are not directly available in terms of metals. For example, let us take any kind of a metal, it is not available in terms of a direct metal. Like for example aluminum, iron, all those. These are available in terms of ores in nature. So we do some process, we extract them and we develop materials. So that's why all these called man-made materials. This polymers, ceramics, metals. And natural materials, what are the different natural metals which are available in nature? So in the nature, we have mud and clay. We don't do any kind of a processing which are available in the nature. These stones, skins, wood materials. In wood, different kinds of woods we have. Softwood, hardwood, different kind of plants. So all these kind of natural materials. So why I start this slide, the topic with this slide is, from the ancient time, we have materials. We used that materials. Once the civilization started, we changed the materials. Nowadays again there is a boom like go for natural materials, use natural materials, reduce plastic, don't use plastic, all these things. Means again we are seeing towards the nature. So that's why I start with the slide with the natural materials and man-made materials. So this slide generally everybody sees. Whenever you study any materials concept, we'll start with this slide. Like we have metals, plastics, ceramics and composites. Whenever I talk about composites, I'll show this slide and then combine the concepts. For example, metals, we have ferrous, non-ferrous, amorphous. I don't talk about the more about the classification related to it. So these particular metals combined with plastics, like a metals in terms of a powders, combined with the plastic, forms a composite. That's called metal matrix or metal filler polymer composites. Later we'll talk about more about that. And these plastics combined with ceramics, either the oxides or carbides or any other materials in a powder format. If you mix into polymers, either it may be a thermoplastics or thermosets, we get composites. Okay. So combining metals and plastics or plastics and ceramics or metals and ceramics gives you composites. The third one, last one. So what is composite actually? It's not a new one. Before going to that, so how you understand a material? What are the basic things to understand a material? Like for example, there are n number of materials. Earlier slide I said natural materials, man-made materials. We have different kinds of materials. Right? So to understand the material, what we need to know? We need to know the properties. So we need to know the properties, like properties of the materials. As I'm a mechanical guy, so I show first one is a mechanical properties because my field, right? So I show mechanical properties. Generally, everybody studies physics. So generally starts with physics. Okay. So physical properties we have, and after that chemistry will run more. So chemical properties. From the schooling we do that. Physics, chemistry, these are the two. And biological properties. In metals we don't do more biology. Okay. So physics, chemistry. After that comes to mechanical. This integral part of this physics and chemistry comes to mechanical. And there are other fields. If people are from the different fields like tribology, some other categories. All these properties, once you know all these properties, then we understand the material better. Any material, if you understand all these properties, then we can understand that material. We have a n number of materials. For each and every material, if you start learning all these properties, it's a very difficult. And comparing the properties and then correlating it, this will be very difficult. So these are the few properties to understand mechanical, like strength, toughness, hardness, ductility, elasticity, fatigue and creep, physical properties, density, hardness, and other thermal conductivity, all those properties. And chemical oxidation, corrosion, these are the terms. A few more. Coming to composites, why composites? Because as the topic is about composites, I slightly jumping into the composite materials, not talking more about other kind of material, because the concept is about nanomaterials. If you start talking about materials and then their properties, their classifications, then the class will end. So I directly jumping to composites. Particularly first, why, what fundamentals are required, how composites are different from other engineering materials, and what constituents are presented in the composites, what are the different constituents present inside it. Because we have metals, we have plastics, we have ceramics, then why composites? What are the other constituents? How it is prepared? What are the advanced technologies in the composites? And how composites are manufactured. So these are the topics, terms. If you understand this, then we can understand the composite easily. But up to now, I didn't say about what is the definition of a composite, what are the terms inside the composite. So we'll go to that. Before that, as I said, material evolution, I'll start with the material evolution, right? So I just given a graph, this is taken from online. So I started with 10,000 BC and the present 2020. So this graph shows you 10,000 BC to present trend, what are the materials, how the materials are evolved. If you see the graphs, I talk with first one metals. As I said, in the ancient time, 10,000 BC also we have metals. Then that time also we have metals. The first one what we have is a gold. Nowadays it's a very costly one. Among all the metals, if you see, we can purchase a gold because it is very costly. But at that time, the first metal what we have is a gold. People start developing different components with the gold. The disadvantage of the gold is it a brittle or ductile? It's a ductile. If it is a ductile, easily it will bend. For structural applications, for other applications, we can't use it. So people start develop the gold. There is no applications. They start seeing other materials. In 5000 BC, after 5000 years, they developed copper. They start using copper. Copper is also, it's a ductile, but when compared to gold, it's somewhat harder. When compared to gold, it will be somewhat harder as a copper. They developed copper, after that bronze. Finally, they identified iron. Once the iron comes, all the structures, all the materials and the entire world, it is changed with iron. Because they earlier used with the bronze. In any old movies, if you see it, all the components in the bronze only they show. Olden movies. Some, if it is not old movie, somewhat related to some 90s or something, they'll show more iron kind of things. Aluminum, iron, all those things. So iron comes into the picture. After that, we have a cast iron, steels, alloys. After this, we have more alloys here. Present trend, this is a blank. We don't have more metals. Why we don't have more metal means there is an industrial revolution. That industrial revolution starts changing the metals. Whatever the metals we have, people start changing the metals because the weight of the material is high. So therefore, one small question here, like why this material is changed, what is the need. For example, simply we will take one example, how this particularly aerospace is modified. If you take like when I started like 20 years, 15 years back, when you want to go from Hyderabad to Delhi, the aeroplane cost is high, travel distance. The distance and in the aeroplane the cost of the ticket is high. There are few reasons. Number of passengers will be less and fuel consumption, all those parameters are there. Nowadays it's become very less. That days 20,000, now it is 2,000, 2,000, 3,000. So the distance is same, the flying heights are same, everything is same. Only thing modified is materials. Earlier we have full metals, now we have full composites. So all the aero structures are modified with the composites. Composites are the lightweight materials. Due to that, fuel consumption reduced and maintenance reduced, aeroplane cost reduced, finally ticket cost reduced. So this is the logic. So the materials are evolved from metals to polymers. So next concept is about polymers. Again, polymers are not a new materials. These polymers from the ancient time we have. There are wood materials, skins, leathers, all those things. Ancient time we have it. After that, people didn't use anything. They used only glues, some kind of gum. After that, rubber. Up to 90s, 1900, we don't have anything, particularly polymers. In 1940, when there is a Second World War, people start using plastics. In the First World War, they used metals. In the Second World War, they used plastics because there is a radar technology that time identified, and then to they don't be detection, they used polymers. They developed polymers. So they start using polymers. From that day today, we are using more plastics, polymers. So we have, you can see it from here to here, all are plastics. Nowadays also we are using more plastics. Only one concept is, nowadays there is a slogan like reduce plastic and don't use plastic, all those things are coming. Next one is composites, our topic, whatever I am discussing now. So the composites also are not a new one. From ancient time we have, if we have a plant, the plant is a composite. Our human body is a composite, but we don't know the terms. Okay. So these particular plastics composites we have. After that, in the entire line you can see there is no composites. In 1940s, at the time of Second World War, they developed GRPs, glass fiber reinforced composites. They used plastics, glass fibers to develop structures, aerostructures. They used it for the aeroplanes for a fight, Second World War. So that time they used it. After war, again they continuously they are not doing the wars, right? So what they have done is they shifted to industrial revolution. They changed all the metals with the plastics and composites. Nowadays, if you see any high-end cars, high-end equipment, all there we have a carbon fiber composites or glass fiber composites or Kevlar fiber composites. So about composites and ceramics, from ancient time we have different materials. So coming to this evolution, simply in the diagram, like I give an AI ChatGPT, like to give a evolution of a materials, it gives like this. It shows like the Stone Age we used a wood and stone. You can see it here. This is not a iron, this is a stone. If you see the old movies, that time they'll take a long stick and then on the corner they'll fix a stone. They'll wrap it. That's what they given in 10,000 BC. It's a Stone Age. They use stone. After that, Bronze Age, they use bronze. After that, Iron Age, they used iron, the hammers and all those things. Nowadays, polymers, we are using more plastics. In the future, we are going for composites. So in that, it assumed and then given an image from 10,000 to present time. Okay. And ancient side, like I said, like what are the ancient composites, what exactly it will give. It shows mud straw bricks. If you see the history, I think everybody in the movies are real. You might have seen it like Colosseum or Roman culture. They constructed a long back, almost thousands of years. Their buildings are intact. What is the construction, particularly what we have in our India, in our other parts? We have our houses, our buildings, whatever building we are sitting now. It's hardly, it will be 100 years. Why this is 100 years? Where we have iron, stones, and the construction cost is high. Everything is high. But their construction in their olden ages, they don't have technology, they don't have anything. But their constructions are still remains. What is the difference actually is, their bricks, whatever the construction they used, this Manstra bricks, they consist of 9 to 10 different kind of materials. If you see the crack propagation or any techniques related to mechanical terms. So for example, in the failure, if any crack started, the materials which are having a new thing, it stops the crack propagation. It won't allow it to deviate. It allow it to break. So that materials, 9 or 10 materials, won't allow it to degrade very faster. That's why that particular structures still also we have. Our structures, whatever the cement bricks what we have, or normal bricks we have 1 or 2 materials. If one material have the crack has a capacity to break it, the entire structure will be gone. So other things, pottery and then wood, the wheel concept. I think if you are interested, you can see the wheel concept. When the wheel is evolved, nowadays whatever the components, whatever the equipment we have, transportation, everything, that depends upon the wheel concept. Once they develop the wheel, they will get. And finally the mud, the bricks. For a real image, this is 13,000 BC Egyptian technology, they used these bricks. Right now also we can see it. In Egypt still it is there. It is not decomposed, it is still in there. And in 12,000 AD, and jumping directly to Egyptian to Mongolian culture, they used a bow. That time, nowadays if you develop a bow, arrows or anything, with all the technologies, we can't send an arrow for almost 1 kilometer. That time, they don't have all the technologies. They structured this bow and they developed the bow. To develop that single bow, it takes almost 1 year. So they use 9 to 10 different kind of bamboos and other materials for that, and they developed this bow. That's why the popular, like if you see any Mongolian works, they use only bows, arrows. Okay. So that is one of the composite. That time they don't know the word of composite, but they developed it. This is said like evolution of materials at the time of Second World War. In the World War, you can see these structures. In the First World War, those are iron. They developed with the plastics. After that, they used it for putting the bombs in the different places. They used it for a war. And simply I have given like evolution, how it happens. 1940s, we have woods and fabrics. 1940s to 1960s, we have low carbon alloys and other materials. 70s and 90s, we have again fiberglasses and alloys, and carbon composites, natural fiber composites, now nanocomposites. So with this, like some few examples, like what are the day-to-day applications what we have, exactly like in a day-to-day life what we can see related to composites, like concrete, straw bricks, wood and everything. Why particularly these composites are necessary? What is the use of it? Why we need to use it? In this particularly, it have a high strength, high stiffness. These are the different properties which differ these composites with the other materials. So again, the definition of a composite. I think everybody knows alloy, right? Have you heard the word alloy? Alloy means, generally the definition says combination of two or more metals to form a material, a new material. In the composite, the definition is same. It's a combination of two or more materials or metals. Then what will be the difference between an alloy and a composite? Here comes like, if an alloy is, if you combine two metals, you form a new alloy which having a new properties. The entire material will be a new material. When it comes to a composite, two materials will be joined together. They don't lose their original properties. They act as a single material. We can easily separate it. Once an alloy is formed, then we can't separate it. We can't separate that material alike. But when it comes to the composite, when two materials are combined and form a new structure, that particular structure can be separated easily. So that's the difference. Again, this same like history of composites is given, and types we have a polymers, metals, ceramics and natural fibers. And here in this picture you can see it. We have a reinforcement, these are the reinforcement, and this is a full matrix. To understand composites, I hope like few are already working on it, few probably these words will be a new things. Okay. So if I ask you like any example for a composite, let us say one example generally in the class I will say regularly. Everybody say see cricket, right? Everybody see cricket, play cricket, majority of the people. So when you see the bat, if it is a two halves, one is a handle, another one is a bottom, one is a bat. If two halves is separated, then how we can fix it? Handle and the other halves, two halves is separated, then how we can fix that? Gum. Okay, one option what is that is a gum. Where is gum? Anything? Any other? Nails. He said nails. We can fix a nails and then with nails. Okay. Any other? Threading. Directly we will put threads. Threads and vehicles. Okay. Any other? Any other things?
When we make an incision on the body of the bat, we can fix it instead.
Fix it?
Fix the handle in back inside the body. Make an incision, like something like an arrow or something which stays. And you stick it.
Stick it with what?
With gum.
Gum. Any other? Fine. No, we have different answers. Let's come with one by one. Someone said gum. We'll fix the two halves and put a gum. Now the problem with that is gum having a less resistance. When you start again playing it, whatever the ball with a different speed hits the bat, because you are sending your energy, right, to hit it, then your energy is sending through your body, and the opposite side ball is coming with the speed. Once it hit the bat with your energy, its opposite reaction, the two will be separated because that particular gum won't have that strength. Now the gum concept is gone. We can't use a single gum. Next one, someone did nails. If you fix the nails also, that nails already damages the surface. Surface damages the handle as well as damages the bat. When two are damaged, then we can't use it. Next, someone said we can use threads as well as gum. So here, if you use the threads, if you roll all the threads on the top of a bat, on the handle, and pour the gum, equal portion, then gum will be in a liquid state and the threads are in a dry state. These two will be bonded together and these two will roll on the handle and the bat, join these two halves. Then whatever load you are transferring, you transfer to the threads with the handle, and that is already connected to the lower bat, and these two are bonded with the Fevicol and threads. So the load transformation won't happen through the polymer gum. It transfers through the threads. All the threads act as a reinforcement and the load is transferred to the lower bat. It never separates. So here in the concept, if you want to separate it, put in a water, the gum will again convert into a gum. It will be liquid, come out, all the threads will come out. So this composite, the combination of threads and gum make you a composite. This can be separated easily and can join together easily. Okay. So only thing is these threads are reinforcements, gum is a matrix material. So in a composite we have reinforcement and a matrix. Matrix always transfer the load. It won't carry the load. It always transfers from one body to another body. Reinforcements always carry the load. The reinforcements are the threads, matrix are the Fevicol. So Fevicol always transfer the load and these reinforcements carry the load. So whatever the load which we apply, that always carried by the reinforcements. Okay. So that's why in this image you can see it, there are two phase matrix and reinforcement. The reinforcements always carry the load matrix always transfers the load in between the reinforcements. What are the different types of matrix we have? Quickly I am going like, because as we have the nanocomposite, later we come to that topic. So we spend more time on the nanomaterials, nanocomposites, less on composites. Because if I directly start to nanocomposites, if you don't know composites, then there is no use, because you don't understand that concept. So bringing to first metals. If you use metals as a matrix, we call it metal matrix. If you use polymers, polymer matrix. If you use ceramics, ceramic matrix. So in all these three, we can add a new material as a reinforcements. Because sometimes like these metals won't have a high strength. There we need to add some materials which can modify their properties. For example, let us take aluminum. Aluminum is a ductile or brittle? Aluminum is a ductile material. So what about the hardness? Is it a higher or lower? The hardness of aluminum, it will be lower. So if I want to increase the hardness, then what I can do? To increase the hardness of aluminum, what we can do?
Add another.
I think there are some few treatments, like for example, like a quenching, heat the material to the higher temperature, put it in the water, so that oxides will form on the top surface, which changes the properties, increase the hardness. That's the one concept. But what we are doing is, we are spoiling the entire material, we are changing into oxide. The aluminum is converted into aluminum oxide, we are changing the material. Instead of that, if you add only a coating of a top of layer, add a ceramic coating on the top surface, where particularly the surface will be modified. Then it is called a composite, surface composites. On the top surface of a single layer, we just inserted silicon carbide particles. On the top surface, it will be modified. Then the hardness we don't get for the aluminum. The hardness we got for the ceramics, composites, SiC. Silicon carbide is inserted on top surface. That top surface gives you a more hardness. Hardness is increased for it. So on the particular location only, we are increasing the hardness. If we need a hardness in the entire composite, then what we do is we develop a full composite, not only on the surface. If you need only surface, we develop surface composites. If you need a full, we insert all the particles inside it. So in the metals, if you need increased properties, we add some other materials. In the polymers, if you want to increase same concept, we add some other materials, either continuous fibers, glass fibers, carbon fibers, different kind of materials we add, and we can do it. And ceramics also same. How many of you seen like Formula 1 cars? F1 race. So is it a metal car or what kind of a car it is? It's a metal material. Carbon fiber reinforced. What will be the approximate cost of it? Billions in terms of crores, like 1 crore, 2 crore?
No, sir. Around 100 crores.
100 crores?
Yes.
I don't know. If it is 100 crores, nobody participate in the race, like where damage is 100 crores done. Now, like when you see a Formula 1 race, when it is going on a track, sometimes it will call means 100 crores done.
Yes, sir.
Yes,
The
sir.
prize won't give you 100 crores, right?
Yes, sir.
If you win the F1 race, they won't give you 100 crores.
No, sir.
Then why is it like I'll take a 100 crores vehicle and then spoil it, and then I'll take a 50 crores?
Sir, they are building a technology.
No, it's not a technology. Actually, that racer cars also it comes of 5 crores, 10 crores. It's not like 100 crores. Because the prize money is not 100 crores. Whatever the prize money they will keep it, it won't be 100 crores. Because the carbon fibers, what we get, for example, okay, maybe some vehicles, if they go for a higher end, there maybe it's not 100 crores. If 100 crores, nobody will participate in the race. Okay. For example, if you see like, if I say like, we don't talk about like racer cars. If I say a bicycle is 10 lakhs. You keep it outside. You don't sit here, right? Because cycle is outside, which is 10 lakhs. If I sit here, then my mind is there only, right? There are 10 lakhs, kya ho gaya, like bar hai. Okay, I don't sit here. Even if I put a lock also, I always think. Because somebody will carry it, right? It may be 10 lakhs means very light. You will take it and you go out, then 10 lakhs there. Then imagine like if it is 100 crores, let's make you like. Okay? So there is a 5 crores. That is a 5 or 10 crores. So if you say that 5 crores, the weight of that particular racer is very less. That's why it moves very faster. High speed. When you go high speed, there is a drag, there is a high friction that can need to be sustained in that high speed. So for that, you need a high strength materials. So they use carbon fibers. So the cost increases as you use more quality carbon fiber materials, okay, for the composites. So we combine different materials. This is, as I said, like every time if I said a glass, everybody confuses what is a glass, because from the maybe yesterday or earlier he is talking about crystals and all those things. Probably I thought like if I said glass, you think about that glass, this glass is different. Whatever the glass, what you crystals, all those things are different, this is different. But this is same, similar glass, E glass, S glass. This glass is extracted from that material. So the extraction process is, this one. Melt the glass. I think many are working on bioglasses. Melt the glass, extract the fibers, and make this kind of mats. It's a bidirectional or unidirectional mats we develop using that glass, extracting a thin fibers from the molten material and prepare this. The strength of these fibers are, it's around 3200 megapascals. If you see any kind of a metal won't give you 3200 megapascals, any material. This gives you that, but as an individual. If you combine it with some other thing, it will be gone. Means it's like our shirt. If I wear a shirt with that material, fine. If I want to apply any kind of a load, it won't sustain that, because it won't have stiffness and other properties, mechanical terms. So I need to combine with some other thing, some other polymer, some other metal or some other material. When I combine it, it won't give you 3000. It will give you 300. So that's why we don't have more that. And it will be very less cost. These are carbon fibers. Again the same thing. As I said, racer cars and all those high-end applications, we use this particular carbon fibers. This particular low grade carbon fibers gives you per meter 3000. Okay. If it is a per meter 3000, if I want to make a plate of a meter of a 10 layers, then assume it will be 30,000. If I want to test it for it, then it goes in terms of lakhs. For a glass fiber, it is 100 rupees nowadays. We can go for any kind of n number of materials, we can test it because the cost is low. Okay. So this gives you around 6,000 megapascals. So you can imagine like a glass fiber 3000, it gives you 6,000, means double of it. That's why for racer cars, for high-end applications, for space applications, they are using this one, carbon fibers. Okay. Have you heard a bicycle costs you around 50 lakhs, 60 lakhs? Have you heard about a cycle? Cycle costs you 50 lakhs. So in that, they use this kind of a high-end carbon fibers with the 3 pegs. Directly they will make a single structure with the carbon fibers. The entire cycle will be a single structure. So that's why the cost will be very high. You can lift it with a single finger. The entire cycle you can lift with a finger. That much lightweight. They use it for racing cycles. They need a high strength with a lightweight. They use it for that. Okay. So again, classification, just for idea, I is just giving it. How the fibers can be layered: unidirectional, bidirectional, multidirectional. Why we go for multidirectional? Because as a mechanical, we'll see like there will be a dynamic load. For example, if I am moving, different kinds of loads will come. For example, when I am walking, friction will develop below my feet, air will hits me, and some other forces from other direction. So dynamic loads happens on my body. So if I develop a material with a multi-directional one, then it can sustain further. For example, if I have any only friction is talking about, like on the lower, when I am walking, only I talk about friction, then I will go with one directional materials, because only one condition. When I talk about the air, some other loading conditions, all those parameters, then I need to go for a multi-directional. That's why in the technology, in the terms, when we change the concepts, we develop new materials, like multi-directional materials. Okay. So how many of you heard about functional graded materials? I think you don't have it. Thank you. Others, can you raise like hand? You raise your hand, like how many of you heard functional graded materials and a short form FGMs? No. Okay. Smart materials. Smart materials. Shape memory always. Nanomaterials anyhow, like from the 2 days we are talking, so I don't ask that. Any other like new materials? So like why functional graded materials? Let us last in the tomorrow's class I'll talk about that. Why functional, what is functional, all those things. This one will skip it. Yeah. Have you heard hybrid? Basically in a plant we heard about hybrid plants. What is that actually? What is a hybrid plant? Generally we heard about hybrid bananas, hybrid something, hybrid fruits or something, hybrid plants. What is that actually? So genetic engineering we can say, genetic engineering, that one kind of a species we can take it and then mix with some other species where we can develop more materials, more terms with a lesser height, all those things. That means combining two different kind of same concept materials and then making a new kind of materials, that is called as hybridization. These particular composites will go for hybridization. That hybridization terms tells you like wherever we have a less strength material, we add it into polymer. For example, let us take give an example of bat threads Fevicol earlier. Still that threads what we added won't give you that strength to sustain the ball force. When a ball is coming and then we are hitting it, that ball won't sustain for that. So in that case, along with this particular cotton threads, if you use a silk threads, one layer will be a cotton, another layer will be a thread, silk, then the silk having a high strength, high stiffness. So with these two combination, the strength will be enhanced, doubled. So that is called hybridization. In one layer we have another material, the other layer will have a different materials. So two different kind of materials, that called as a hybridization. So here in the simple example you can say we combined one bamboo sheet, one glass sheet, one is a natural one, other one is a conventional glass sheet. So we combined two different materials to replace glass. In different fields already we have a glass composites. To replace that particular glass, we used a bamboo sheet. One is a bamboo sheet, another one is a glass sheet. We hybridize the materials and we'll start testing it. So that's called a hybridization, combining different kind of fibers. The another concept is a filler concept, adding a fillers to materials. As I said, like silicon carbide coating on the surface. So probably everybody has seen metals and all those things in terms of rods and other metals. So here metals are available in terms of powders. Aluminum, carbon, magnesium, titanium dioxide, zirconium dioxide, all these we can fix it, add to a composite. In a polymers, in a metals, ceramics, we can add all these things. So coming to the concept of nanocomposites, as exactly like related to our concepts, nanomaterials. So we see nanocomposites. So I think already when they talk about nanomaterials, nanocomposites, nano concepts, have they talk about like how small it is? How much small it is?
Less than
10 to the power of -9. How much small it is? 10 to the power of -9 is a mathematical term. How small it is? 1000 times of microns or something. How small that is? Because we need to know, right? Like we are saying mathematically. If I am not a mathematical guy, I don't know 10 to the power of -9 means I don't know what is 10 to the power of -9. Name some material which is nano. No. Huh?
virus.
Virus. Okay. Virus is a one material which is in nano level. Okay. Good. Any other? Dust particles. Yeah, dust particles may be in the nano level. Any other things? A bacteria. So before going to this one particularly, I'll show a small comparison. This will be interesting, like, to understand it. This one. Because if I start with the bigger one and then go to the slower one, then we can understand. Because even in the anything, we will start easily comparing with others, right? He had something, I don't have something, all these things. Like this, I just made a small comparison. You can see it like this is the largest star. These slides are old. Don't say that, sir, now the new star and the chat GPT I just typed the new star already bigger star is there because it's a old PPT. So when I prepared this one is a VV Cheppa is the largest star. I just compared that star with the sun. How many times you can see it? That is 1900 times. That's the biggest star compared to sun. I just compared the sun with the earth. The earth's diameter is 12756. It's not increased, it's same because the size is not increased, same. So this is 342 times when compared to sun, not with the largest star. And I just, again there are different materials, I don't want to waste time. So I jump to a single child, like a child with 1 meter. So why I chicken tail child means then we have some other terms which are related to the child. Okay. So child is 1 meter, this is this much times 127560000 times. And coming to this micro level, a small coin, a penny, that is 2 centimeters. I think you might have seen raindrop. Morning also we have a rain. So you might have seen the raindrops. The raindrop is 1 mm. What is the least size which we can see with our eyes? Probably in the earlier 2 days, no questions, right? Directly they will talk something and then they go on. Now I am asking that more questions about. Because it's afternoon. If I continuously talk, already you will have a sleep. Then I will get bored if everyone sleeps, right? So what is the least size which we can see with our eyes? A millimeter, like any material, like any name of material, which we can see with our hair. Because already they have last year class. They start in my subject, so they are not telling hair. Here also I have given that hair. So the least size, okay, ठीक है. And now the thing is how you can see a hair in terms of length or diameter.
Length.
In terms of a diameter, we can't see it. We can see that's the least size. In length, it depends upon the length. If it is a higher length, we can see it. Diameter size, that is 100 microns. That is the least size which we can see with our eyes. Below that, we can't see. Okay. So that particular hair, the next one is the red blood cells. As a bulk, we are seeing it. Beyond that, we don't see. Now we are going to a nanozone. When we go to the nanozone, all different kind of materials which we don't want to study, which we don't want to listen, like bacteria, because it won't be good for our body, we don't talk about it. So bacterial phase is 60 to 70, a flu virus is 100 nanometers. So all these are dangerous things. And some other gold particles is 13 to 50 nanometers. The final thing is a DNA, which a human body will be generated. That DNA is 2 nanometers. I just compared with that DNA, and you can see the Earth's one, it is 12756 into 12 zeros. That much small. Okay. So to compare that, how much small it is, we need to take a bigger one and then show a smaller one. Any comparison gives you a better understanding. So, for example, if you see in a YouTube or anything, they will make a zoom continuously and then show a small part and then zoom out. Then you understand, okay, that much small. Two options is either you can see it, making a magnified, or else comparing with the higher one. So that to understand it, I just made this one. So this much small is a material in the nano level. And this much small material, again we are making into polymer nanocomposites, metal matrix composites, ceramic matrix composites. When we don't see our hair's diameter properly, then how you handle that particular nanometer? From the last 2 days you have a different classes, right? Have you asked, sir, the nanomaterials you are saying how to hold it? When we don't see it, how to hold that? How many of you have talked about nano machines or something? In a medical terms, they say always nano machines will be there that cures the cancer cells and then all the things. Nano robots. What is nano robot? As you said, 10 to the power of minus 10. I said like comparison is that much small. Then what is a robot? How we can operate it? How we hold it? 10 to the power of minus 9, which is very small, which we don't see it. Then how to hold it? Because the lectures are going on, you are like listening about all these things, right? Yesterday also just I have a few 1 or 2 minutes he setting about crystals and then the nano level, all those terms. Then the concept is that crystal we can magnify it in a FSCM or TEM, we are seeing it. Then how to hold it, how to use it, how to add to a composite. Because we are saying we have a polymer nanocomposites, metal nanocomposites, means which we can't see how we prepare that. So the definition says one phase will be in a nano level, the other phase will be in a higher level. The matrix, continuous fibers will be in a higher level. Only nanoparticles which we develop adds to it to enhance the properties. So only one phase will be in a nano level, the other two phases will be in a micro level or a higher level. So that is called our nanocomposite. So the one phase which we add to a material says nanocomposites. If it is metals, metal matrix nanocomposites. If it is polymers, polymer matrix nanocomposites. If it is ceramic, ceramic matrix nanocomposites. Coming to this one, I think earlier section about nanomaterials, you have about this nano classification and everything. 0 dimensional, 1 dimensional, 2 dimensional, 3 dimensional. I don't want to talk this. About this dimensions, morphology, state and the composition, all those things. I am skipping this. So just given like what again this one is a chat GPT. Okay. I didn't give a references of it. Then that's what I am telling about this. This I taken this what exactly this in a chat GPT, if I say polymer nanocomposites, how it will be, what representation it will give. This is given like this. So in a polymer, these are the different nanomaterials. We have a 1-dimensional, 2-dimensional and 3-dimensional, 0-dimensional. 0-dimensional are the particles, 1-dimensional are the nanowires, 2-dimensional are the nanosheets. So they have taken different thing and they combined with this polymers and make a polymer nanocomposites. So polymers are mixed with the different kind of particles and they developed it. Then ask what kind of fabrication things can be done, nanocomposites. It shows a solution can be mixed. In the solution we can prepare and melt mixing we can do it, or else polymerization. These three things can be done to develop polymer nanocomposites. Again ask metals, how the metals can be done. So metals, it gives like metals can be mixed with some other metal nanoparticles. This is a metal material, metal matrix, metal nanoparticles and form a metal nanocomposites. Means let us take aluminum, copper nanoparticles, add copper nanoparticles to the aluminum and make a new structure like nanocomposites. Whether it may be using a quenching like melting method or else powder metallurgy method. So in the powder metallurgy also we can do it, or else directly mixing the melting the materials and adding the particles to it. That's called as stir casting. The stirring will be done and the casting will be done. This is about ceramics, how to make a ceramics, combining two different materials in a powder blend and centering and then finally making a ceramic composites. So only difference in all the three are adding a nanoparticles to a metal, polymer and ceramics, making a composite. So now the concept is why nanocomposites. Earlier, have you seen what are the advantages of nanomaterials? What exactly the advantages of nanomaterials? In the earlier sections you have things like nanomaterials, nano advantages. What are the advantages of nanomaterials? It is very small, which is not visible, so it is advantage. Highest strength, which is not visible, having a highest strength. Good, thanks. High surface to volume ratio. Okay, what exactly it is? He is saying like high surface to volume ratio. What exactly do you use?
Catalytic reaction. High catalytic reactions.
High catalytic?
More surface area.
More surface area means?
More reactable.
More exposing to environmental area. Okay, what happens exactly? Fine, as you said is correct. If you have a higher surface, lower particles means higher surface, more exposure to the environment. What happens? What is it advantage, disadvantage?
It depends on.
For example, let us take, I have a very big lid, I am working on it, friction will be very high. For each and every bit will be increased, right? As surface area is increasing, it's a disadvantage. Then what you said is an advantage or disadvantage? Sometimes it's an advantage, sometimes it's a disadvantage. Okay, let us take one example. Let us have one book, please. So let us say, tell me what is the area covered by this? This is, let us take, this is a micron particle. Okay, more than micron. So what is the area covered by this book in this room? If I place on a floor, on a table or somewhere, this is a length, width, that is the area covered by the thickness. So what exactly I will do is, nanomaterials means cutting the materials into a lower level. So which technique we can use to cut the material? Any fabrication technique you have studied, right? Yesterday you have ball milling. Have you seen the ball milling? No. Means earlier you have seen, not yet. Okay, ball milling is what exactly we do? We will put this book in the ball mill and then cut it into small pieces.
Yes, sir. The ball will interact with the material.
Okay, it interacts with it and then breaks the material.
They'll collide.
Okay, let us take, not a bigger one. We'll take a scissor and then we'll cut it. So we cut the material, we separated this one. Now what is surface area? It's a double. Not about thickness, it is increased. I cut the one more paper, spread it here. So if I cut all the papers, if I separate entire thing, it contains entire floor. If I assemble everything and make it, it is a small area covered by it. If I start separating it, entire floor will be covered by this book. Okay, so that's what comes to the nanomaterials. When you cut the materials into lower level, as he said, surface area increases. If my objective is to fill the floor with this book, if I place at one location, there is no use. If I cut it into small pieces, it will increase. That's the first advantage, which I want to show it here. Here you can see it. We have taken a small cube to understand it. A cube side is 5 mm, 5 centimeters or 5 centimeters we can take. What will be the surface area? It has 6 sides. One side will be 5 into 5. 5 into 5 into 6. The total surface area is 150. What we have done is, we cut this into 5 horizontally and 5 vertically. Then it becomes a 1 cube, 1 mm cube, 1 centimeter cube. 1 centimeter cube, each cube, the surface area is 1 into 1 into 6, 6. When I cut 5 horizontally, 5 vertically, then I will have 125 cubes. That 125 cubes into 6 gives you 750. Means, when a larger particle is there, it occupies certain area. When I cut that into smaller pieces, surface area is increasing 5 times, 10 times, it depends upon the number of cuts. So the surface area is increasing continuously. After that, the next advantage, just we have taken a composite. This is a polymer plate. In a polymer plate, I fixed a particle here. What is this black portion? So this is entire polymer plate. In that we added one particle which circled it with the black. What exactly that is? I am holding this particular pointer with 2 my fingers. What exactly between my fingers and this pointer, what is that interaction?
Electromagnetic.
Van der Waals force.
Electromagnetic interaction.
Electromagnetic interaction. Any other thing? The simple thing is, there is an interface. I am holding it. Just simple. I am just holding it. In a single finger I can't hold it. Okay. 2 fingers I can hold it. Then what is the chance? There is a chance of falling of this material very high. 3 fingers, interface increases. 4 fingers, more interface. 5 fingers, more interface. If I hold like this, better holding. So what exactly is happening is, the contact point between my fingers and the pointer is increasing, interface is increasing. Okay. So this is called an interface. This black region is an interface between the polymer and the particle. What exactly we have done is, again we put this particle in a ball mill, cut into small pieces, we cut and then distributed inside the plate. So same particle, the area what approximately we covered is of 6%, the interface is 4%, the black region. So we cut into small pieces and then distributed here. The total area remains same because we are not adding a new material. Only what we are doing is we are cutting it into small pieces. So the area remains same. the black portion which covers this particular area is increased to 45 times. It's an approximation. It's not exactly like we didn't measured it. Approximation 45% means the interface area is increasing with this one. So one advantage is surface area. The second one is when you go to nanomaterials, interface. The third one is, how many of you studied about crack propagation or understand about crack propagation? Have you heard the crack, right? What exactly that physics people, I think different people are there. Just like you have crack, for example, to understand it simple, I think these are some kind of a wood and different kind of thing. If you see a normal wall, outside of this wall when you have a break, we can see a wall, on the top of a wall, there is a big crack. Means breaking of a wall, like we have a crack on the surface. Once a crack is formed, in which direction it will propagate? In which direction it will pass? Where there is a weaker section, weaker material, in that direction it will pass. So, in the particular weaker section, if you have a new material which are stronger, then it won't pass. It will restrain some time. So here you can see it, if a crack is started here, comes here up to here, it breaks the interface and passes through the entire material, break it easily. So the life of the material is very less. It's the same condition, if it is initiated here, every time to pass to this end, we have 5 to 6 obstacles. Every time it has to stop, take a new direction or pass through it. So to break that entire structure, there will be a 6 obstacles, here 6 to 7 obstacles, here we have only 1 obstacle. Once it breaks that obstacle, the entire material will fracture. If in this condition we have a 6 to 7 different materials which stops continuously the crack. So that's why the life of the material will increase. So as I said in the first starting example, the ancient time, the bricks, they use 9 to 10 different kind of materials. They used animal waste, bones, eggshells, sand, different kinds of sands, different particle sizes of sands, rice straws, all those things, 9 to 10 different materials they used it. Each different material have a different properties. When they combine all the materials act as a single material. To break that material, if any crack or anything comes, they have to break all these properties. So that's why the life of that particular bricks are very high, thousands of years, still it is intact. Whatever right now bricks what we have, it's a consist of only 2 or 3 materials, like one kind of 2 or 3 kind of materials, 2 3 different kinds of a sand. So once it have a resistance to break that, it will break the entire. That's why we'll have a 50 years or 100 years life. So the crack propagation is another advantage with this particular nanomaterials. So let me have a break or continue this. Continue. If it is okay, then we'll continue. Like otherwise, we'll take a break. What's the time? So 3:20. The 1 hour is done. So if you want a break, we'll go for a break, and then we'll continue 1 hour. Is it fine? Please check it once. Now. Okay. Like once we get something.